Okay, the next team is Team 6, Personalized Lighting, with the acronym Pilsner.
Stealing my jokes.
I'm not stealing your jokes, okay? Because I'm not very good at that. The customer is Professor Tom Little, who's also the director of the Smart Lighting Lab here at Boston University. So with that, here is Team 6.
Hello. Good afternoon and welcome to Pilsner, not the beer, but the new personalized immersive lighting system. My name is Tom Murphy. This is Koenigsknecht, Andrew DeNicola, David Chang, and Brian Meyers. And today I'll begin by talking about the project objective and system overview, and then Brian will go on to the control system and the server. Next, Ian will go on to the user interface, Andrew will talk about the sensor unit, and finally David will talk about the energy-saving techniques. So, there's one objective that many modern-day engineers have been working towards. This is energy-saving techniques. We are looking for new energy-saving techniques that will not only make it simple for a user, but also make it transparent to the user so they don't necessarily realize they're saving energy until they receive an electric bill. The other objective that many engineers are striving for is user comfort. We are not looking to create an environment in which a user is comfortable, but we are looking to let the user themselves set that environment for their own personal needs. So for our final project, we've combined these two objectives into a comprehensive, stable, new lighting system that we hope will lead to new research applications within the LED lighting field. So these are our requirements. It comprises of four main parts. The first is our sensor. There's generally supposed to be non-intrusive, small size, sense motion and RGB light. Next is our control function, 1-to-1 light sensor ratio, control intensity and color for each light, and it also hosts the dynamic function, which we will talk about later. The next part is our application, both our web application and mobile application, which allows us to manually control each light. And the last is our server, which will host the control function and provide log data for the viewing by the user. Here's our visualization for this project. So we took those four requirements and made four main physical components of our project. The first is the server, which, like I said, hosts the control function, the brains of our operation. This is connected to our lights by Ethernet or wireless and a router. These lights are high-intensity RGBY LED lights that were created by our customer and his graduate students. These lights shine down on the sensor module, creating a unique feedback loop. And this sensor module senses motion, color intensity, and uses a BLE, Bluetooth Low Energy module, to send information back to the server. And the last part is our user interface, which is present in our web application and our mobile app on the iPhone. So all these components will be explained in detail coming up. Now David will talk about our block diagram.
Okay, so here we have our level 1 block diagram. I'm going to start off with the sensor at your bottom left. So for the sensor, we have our BLE 1112, which reads from the light sensor and the motion sensor. The BLE is also a low energy Bluetooth, so it will transmit the data to the server through a Bluetooth protocol. The server reads this data and then runs it through the control function. The control function then decides what to do, what kind of light controls to give, and then sends that to the router, and the router will send that to the lights. We also have two user interfaces. One is the web app, and the second one is iPhone app. They essentially do pretty much the same thing, but it gives more choices for the user to interface with our system. The user interface allows the user to control the presets and the color intensity, what color lights he or she wants, and like some other side projects that we made, like alert system and also the natural lighting system, which we'll talk about later. And now to Brian about the control function.
So the control function is basically the framework of our system. We use multiple Java timers in our system because timing is very important with a dynamic lighting system. It's important that the lights respond quickly and accurately to this data that we're receiving from the sensors. And it's also important that we know what time it is in the day due to the fact that we have functions like natural light timers that correspond to different light temperatures throughout the day to help your circadian rhythm. Another piece to our control function is an RGB to RGBY algorithm. Our light sensors sense RGB colors only, but our lights accommodate all RGBY spectrum colors. So we needed to develop a way to incorporate the Y even though we aren't directly able to sense it. And what we came up with is we use the Y to basically enhance the richness of our colors. The control function also allows for complete manual control of all settings in the system. Each light can be controlled individually based on color and intensity. And the control function also has to have constant connection with the sensors. The sensors make one connection to the system and then they send data every 0.25 seconds and the system can then react. One of the main things that our system does is when a user enters the room, that's when the system recognizes that someone is in the room, and in that case it will start reacting to the sensors and what's going on. If light sensors are blocked or ambient light is detected, say from outside light, then the lights will actually react and either dim or brighten based on the sunlight or lack of sunlight in the room. Right now our system is it's currently set up to support 4 sensors and 4 lights, but we currently only have 2 at the moment, but it still reacts in the same way. So on to the dynamic capabilities of our system. The first is location detection. Each of our sensors has a motion sensor on it, and it's constantly sending the data to the system, and if there's motion detected, then there's a few scenarios that could happen. Basically what we have is for each sensor that gets tripped, the light above that sensor, the light that corresponds to that sensor will be at its brightest, and it will go down in gradients for each light to its right or left. So for example, if there's 4 lights in the room and say you trip the second light, that light will be at 100% intensity. The lights to its right and left will be at 60%, and the one 2 away from the one that you're under will be at 40%. We implemented this to save energy, and we noticed that it didn't really decrease the actual brightness in the room, and basically it's a good way to provide the light that you need in a room and also save energy at the same time. The second dynamic capability is the outside light source compensation. Like I mentioned before, our light sensors are able to detect the amounts of light in the room, and by that they can judge whether or not the lights need to be dimmed or brightened. When we were coming up with this algorithm, we first were thinking that we'd create a huge lookup table with every single combination of every light color. We soon realized that would take a very long time to do. So we came up with another solution, which is that when the lights are set, they dynamically calibrate to the room and they pull a sensor value. They wait 5 seconds and then pull the sensor value that the room is currently sensing, and then from that, if there are changes in light intensities, it will adjust accordingly. So as a result, there's no setup or calibration initially with the system. It actually happens dynamically as you use it. The third feature is the circadian rhythm feature. We did some research and we learned that it's actually helpful for sleep patterns. and some people that have seasonal disorders, that if they have high color temperatures during the day, which represent natural sunlight, and then lower temperatures at night, it can actually help their circadian rhythm and help them sleep better or get over those disorders. So onto the server. The server is basically a simple read and react design. It's constantly waiting for inputs, and then once it gets them, it reacts. The way that we did this was with the Java TCP server. At first we had it being single-threaded, and then once we realized we would have 4 sensors sending data, as well as a web app and an iPhone app, we needed to multi-thread it so that we could handle multiple incoming messages at one time. We used NetBeans to develop this app, just due to personal comfortability within our group. And it also integrated well with our Java web app, and we were able to share classes in Java Beans and reuse some of our code. Another point is that the server is the central communication point for the system. So all components go through the server, and all of them synchronize to the same information, which allows for just easy reference and also an easy way to keep track of what's going on in the system, and for each component to be able to pull the information that it needs at a current time. And along with our server, we have a MySQL database. And here we have multiple tables, one of which is for the users of the system, for the web app and the iPhone app. Another stores the current light values at any given time, so that if, say, the system crashed or something happened, you could pull up the last light values. Each user can create presets, which we'll go into later, and those are stored there as well. And one of our main features is we store the energy usage data. We came up with an algorithm to basically figure out how many kilowatt hours of energy that you're using. And we did this by using a kilowatt measurer, and we basically figured out how much each color output, and then we were able to develop a table for reference where we could decide how much energy the system was using. So now on to the sensor unit with Andrew.
So I'm going to talk to you a little bit about the sensor unit. This is how our server kind of reads the environmental information. As Brian mentioned before, our sensor unit is responsible for measuring both motion and RGB information in the environment. It consists of 3 main parts. The BLE112 module, which is our Bluetooth low energy module, our light sensor array, and our motion sensor, which is there for some reason, not labeled. Okay, so it also currently runs off 2 AA batteries. We believe with a future implementation of this sensor, we could bring it down to a coin cell to even further reduce energy usage. Actually, I'm going to talk a little bit about each of these components. So the motion sensor is a pretty straightforward sensor unit. Runs off the 3 volts from the AA batteries. It'll pretty much just pull high when a user passes it, and the BLE112 has a built-in ADC port, which can just pull this sensor whenever it needs to. With our light sensor array, it communicates with the BLE112 via I2C bus, so that also has that built-in functionality, so also makes the BLE112 ideal for our situation. For our first revision of this sensor unit, we were using another microprocessor as a middleman between these sensors and the BLE, so cutting that out actually allowed us to save energy and reduce the size of the component. By reducing the size of the component, we could actually meet our customer requirement of a 3 by 3 centimeter unit. If you ignore that huge battery pack on there. The small size of the sensor also allows you to kind of put the sensor wherever you want in the room. So depending on the user's preference, you could either have the sensor sitting on a table at waist height or on the ground, or if you have some kind of adhesive, you could stick them to the wall. So communicating with the sensors, I kind of just went over this, but I thought it would be easy for you guys to look at the picture while we talked about it. So after it samples the sensors every 15 milliseconds, so it can have the most up-to-date room information available. So it pretty much samples the sensors like I talked about before and stores them in its GATT attributes. So it's pretty much its own central database. It's updating its own variables, and so that they're ready for reading at any time when the server requests the information. So then when the server, which has a Bluetooth low energy dongle attached to it, sends a command to request these values, they're readily available. The server interfaces with the dongle through a C++ application, and it's commanded to connect to each successive sensor. This is assuming a 4-sensor system every 0.25 seconds. So in a 4-sensor system, it will know all the environmental information in 1 second. On each connect, the server reads the sensor's relevant GATT attributes, and so it keeps itself very up to date. The application, the C++ application then relays this information, a formatted string, to our control function that Brian mentioned earlier, so it knows exactly how to handle this information. And now Ian's going to talk about the web app and the iPhone app.
Okay, so the way that the user can control the system is through either the Java web app or through the native iPhone app. So the web app is developed on the back end with Java server pages and Java beans. And the front end, so the actual, the looks of it, is developed with JavaScript, CSS, and HTML. And it uses JSTL libraries to access the Java beans. As Brian had mentioned before, there's a MySQL database. We used a JDBC driver, and basically you can have multiple connections to the server. So you can have the iPhone app connecting to the web app, which then sends to the server, or you can have the sensors connecting. And it communicates with the server via TCP. The iPhone app was developed natively using Objective-C in Xcode, and I developed a lot of the icons and images using Photoshop, and it also communicates with the server via TCP using the GCD async socket library. So here you can see this is the presets page for each app. To the left is the web app, and to the right is the iPhone app. And you can see that you can select a preset in each app, and you can create presets, you can edit presets, and you can delete presets. So if you create a preset that sets all lights on, and you later want those to be half on, and you want to change the name, then you can simply go in and edit that preset whenever you want. And once you set it, that becomes the active preset, and the lights then change to that preset. And once you set the lights, the dynamic mode is activated, so it will start adjusting the lights accordingly with the sensor data. You also have manual control, which is essentially the same as the preset mode, but it allows a more direct access to the light settings. So instead of having to either create a preset or go into the presets page to search for whichever one you want, you can just hit manual and set the lights to whatever value and directly send it to the lights. And we can communicate directly with the lights via TCP as well. You can also access all of your energy usage data. So you can see the energy usage either for that day, that month, or in total. And as you can see on the web app, you can also see the current light settings, which is not available on the iPhone app, but it is available on the web app. There's also an app settings page, and here you can change your password for that particular user. You can log out of the user and then log into another account. Or you can set either the sleep timer, wake up timer, or alert timer, which were extra features that we added. So the sleep timer allows you to set a time when you want the lights to turn off. So if you want to turn the lights off automatically at night, then you can set it for 10 p.m., 11 p.m., whatever you want. The wake up timer just wakes up the lights at a specific time. And the alert timer, when it goes off, it flashes the lights in a color that, right now it flashes green, but really you could make it any color. So if you were cooking and you wanted to set a timer, you could set the timer, the alert timer, and the lights would flash green whenever your dinner was done or when your laundry was done, whatever you needed to remember. You can also set the natural light, which is the circadian rhythm function, either on or off in the settings page.
Okay. So basically, these are the lights we're using. They're high-intensity RGBY lights. They run on an Arduino programmable microcontroller using C++, and they control their brightness using pulse width modulation. These lights also run a 12-volt power supply, but the Arduino also needs to be powered too. And they're created by Jimmy and Lucy from Professor Thomas Little's team. So when we compare the two traditional incandescent light bulbs and our high-intensity RGBY lights, you can see like with the same amount of watt, the life of the of LED light in general is a lot longer, and also the lumens per watt is a lot higher. I believe it's 45 lumens per watt for the LEDs, and I think 14 for the incandescents. Okay, so the real world benefit. Now that we've shown you our project, we believe that our project can benefit the world. The system is able to transparently save the user energy. It does this while enhancing the user's comfort through the means of personal immersive lighting. It is also easy to use, and it could be personalized for many users. Think about this scenario. Imagine a room where the system can automatically change the lights when when you're watching TV, so it has one setting, or when you have a party, it can automatically sense that and then like somehow make the colors more vibrant. This is what we're hoping future projects might be able to achieve, and we believe that our project is kind of like a stepping stone towards it. We've already implemented systems such as like the alert system and natural lighting that could, and the circadian rhythm thing that could help promote better health, but there's a lot more that we could do. I also want to take this opportunity to thank Professor Little from the ECE department, Jimmy and Lucy for helping make our RGBY LED lights, Professor Pisano, Professor Kia, and of course our GTFs. We want to thank our friends and families and our friends from Senior Design, and of course BU ECE department. Thank you.
Questions? Yes.
What is the power consumption of the server comparing to the light?
Well, the server is hosted on a computer. Ideally, we'd like to eventually put it just on a router, but the power consumption of the server is just what your computer would normally consume.
I believe it's 30 watts, I think.
It's a temporary fix. Ultimately, the server would actually be hosted on its own device that would be a low power usage device.
Like a gum stick.
But right now, it is just on a laptop just for ease of use and testing.
Yes.
How did you calibrate the lights when it's like really dark and then the lights and then like say if it's not right, then what happens?
Then the lights would dim.
Because don't you have it so that okay.
Well, when you set the lights, it waits 5 seconds and then captures the sensor values, and then that's its reference point. So we assume that when a user sets the lights to some certain brightness, they actually mean for the lights to be that bright, and then they capture those sensor values, and if there's changes after that, then the lights will adjust accordingly.
Okay, so if I'm not going to turn on the low setting at night or the high setting during the day.
Right.
So you mentioned you change your light settings based on where the user is, but you also mentioned you can stick the sensors wherever you want. how do you figure out which sensor, which light to turn on and what sensor turns? Or which light to change over?
Currently, it's a 1-to-1 ratio, so we have one sensor dedicated to one light. Yeah.
So while you can move them wherever you'd like in the room, it should be within a vicinity of its corresponding light. So basically, you can change the elevation and maybe the side of the room that it's on, but ultimately, a sensor is corresponding to one light, and it has to be within its vicinity. You can just change like relative areas to that light.
Does the system adjust for the changing color temperature of the ambient light?
Well, that would be included in the color offset scheme. So if sunlight is coming through the window and it's got more blue light in it, it will know to adjust the blue and the RGBY lights.
What would the added cost be if you wanted to, say, a commercially available light?
Commercially available what?
Light fixture.
If you want to sell it, what would the added cost be? How much extra?
Well, the light fixtures right now that we're using are prototypes. They're provided by our customer, so we don't really have the exact details on how much the lights cost them to make. So we took them into our energy consumption because they are the main system components that's consuming energy. But manufacturing-wise, we're not really sure how much they cost.
So just from a comfort perspective, you have right now 4 distinct sources of light. I mean, how does that actually work in the kind of the actual real environment? Because if you turn on all 4, you should see white, but that's going to, because they're separate sources, going to be dependent on distance.
Well, right now, you can actually see they're not covered. Most overhead lights have some sort of a lens or something that sort of helps blend it all together. You don't actually see the bulb itself. So right now we don't have that, but you can actually see that it blends together. Like at the outskirts, you can see where you have like the red, green, blue, but ultimately we would have some sort of a lens that would help blend it.
The prototype kind of mounting system, I was wondering in general.
Well, like if we had like 4 light fixtures, each light fixture has all 4 colors in it. So whatever color you set each individual light to, it automatically blends. It shows good on our demo out there, but.
You mentioned you have 2 lights, but you can support up to 4. Why is there a limit on 4 lights? Why not more?
Well, the 4 lights that was what was set by our customer. He wanted us to have at least 4 lights. And the reason we have 2 is just because that's all that they could build for us.
Well, my point is there a reason you shouldn't support more than 4 or can't
Well,
support more than 4?
ultimately, we would like it to support more than 4. If it were a final product, like if this were commercially available, then ultimately you wouldn't have to have the 1-to-1 ratio. We would have a way for you to sort of map the room. But as it stands now, it's hardwired to have 4 lights and 4 sensors.
Also, that number is kind of chosen because that's how many ports we had available on our router at the time.
Yeah.
But it is scalable. I mean, you can
Yeah.
scale it.
Yeah, definitely.
I mean, you're not,
It can control as many lights
nothing
as.
fundamentally limiting you. I don't
No,
think.
that's just what we have it at right now.
Right.
I mean, I think that's one of the issues.
Yeah.
If you're going to use.
4 is pretty
something
arbitrary.
like that, you're in this room, you probably have more than 4.
Right.
Thank you.
Is this running off?